that, I give you Tim Rose, and thank you so much, Tim.
Thank you, Cindy. So my talk today is a little bit short. So I decided that I would throw in a couple of slides because of the time of year we're here. About 6 or 7 years ago on this very day, I happened to be in Mexico for geologic reasons. So that makes it okay to show these. But anyway, on the morning after November 1st, if you visit a cemetery in Mexico, this is what you might come across. Of course, this is after the great celebration the night before called the Day of the Dead, but it's really a fantastic thank you to all the people that came before us. And anyway, I just thought I would throw these in because I need to lengthen my talk a little bit, and because this is what it would look like if you were in southern Pueblo State this morning. So if you followed that trail, or if you were a spirit and you followed that trail of marigolds, you might come to a big installation, ofrenda like this, which is set up to remember specific people who have passed on. Anyway, back to the real subject. So as Cindy said, as a kid, we would collect rocks anywhere we could. And being a resident of Montgomery Village, that meant the riprap that was around the pond overflows. And we found these great rocks that included minerals from the Hunting Hill Quarry, also known as the Rockville Crushstone Quarry. Which we couldn't visit. So the best thing we could do was visit these boulders and gravel parking lots and places like that. And sure enough, we could find some interesting things. And in 1969, this fellow from the USGS named David Larrabee published this nice study of the rocks at the Hunting Hill Quarry. Hunting Hill is a place name that I think is now lost. I drive through it very frequently, and there's no sign that says Hunting Hill. It's really in Rockville on the edge of North Potomac and Gaithersburg in Montgomery County, Maryland. And here is Montgomery County. Down in the lower right, you can see Washington, D.C. and the coastal plain rocks that make up the bedrock there. Everything to the northwest and up this way is the Maryland Piedmont. A little bit of the Triassic Basin up here where dinosaur tracks can be found, much younger rocks. And these are the complex metamorphic rocks of the Piedmont. And what you see, here's Gaithersburg right here. Hunting Hill is actually shown on this old map from, I think, 1968, which is the part of the state map of Maryland. And what you see in this section of what's called the Wissahickon schist, you see these pink things. And there's the UM there. Well, that's for ultramafic. And these are rocks that used to be probably part of the mantle, made out of minerals like olivine and pyroxene and maybe some plagioclase and garnet. But they've been metamorphosed. Of course, that means they've been squeezed, they've been heated up, and those minerals have changed, which is the basic meaning of metamorphism, right, to other minerals. And the main bodies here are what are called serpentinite bodies. And this is, in fact, the Hunting Hill body right here. Montgomery County again, here's the box here shows what we're looking at. This is actually showing that there is now a park right next to the quarry, which is right here in the very center. So there is public land that you can go visit. Serpentine Barrens Conservation Park. There really aren't serpentine barrens here. If you want to see true serpentine barrens, you need to go up towards north of Baltimore and visit Soldier's Delight, where there are, in fact, plants that only grow there because of the coarse soil that occurs on top of serpentinite commonly. There aren't such a thing in this particular Hunting Hill region. Here's a map, an aerial view, I mean, and here's that parkland, and there is the big hole in the ground, and there's my house. So it's not far at all, a couple miles from the quarry. There's another serpentinite body that goes right behind my house. It outcrops in the Kentlands area where they had a lot of trouble digging basements because of the serpentine that was exposed there. Anyway, there's the huge hole in the ground, and you can even tell that it's got kind of a blue-green color. I find that pretty amazing. Here's what the outcrops in the park there look like. These are serpentine boulders right on the surface of the ground. And thanks to this fellow Larrabee, we know what the cross-section of the quarry, the walls looked like in 1969. And what you see here is, looking at this nice line drawing, you see that the wall is made up almost entirely of serpentinite, and I'll explain what that is in a minute. And then there are these dikes. Well, a dike is a younger rock that has intruded into an earlier rock. And, you know, Andy was wondering how people knew where to go look for the goodies, but this is kind of telling us where to go look right here. These dikes are, in fact, where a lot of the nicer minerals are found at the Hunting Hill Quarry. So, as I said, most of the quarry is serpentine. Here's a neat piece of serpentine, sometimes called picrolite. There's also chrysotile asbestos there in very thin veins. Some of the other minerals, this is a piece I collected many years ago of prehnite with some aragonite sprays on the top of it. This is clinozoisite that has been etched out of, this is a calcite here in the remaining here after dunking this rock in hydrochloric acid for a couple days. Here's another one of those. And here's your scale bar down here. That's 8 inches across there, or 7, of a very odd mineral called coalingite. And the Rockville crushed stone quarry is very well known for this mineral because of the size of the masses that are found there. So if you're lucky when you're there, you might find this sort of bronzy looking, really odd magnesium iron hydrocarbonate mineral. Very unusual. There's also blobs of common opal, but the big cheese, as mentioned earlier, are these beautiful, sometimes gemmy, grossular garnets. And these occur in cavities in those dikes that we were just looking at in the picture from Larrabee in the walls of the quarry. Now, I'm going to stop for a second and tell you about the asbestos for a minute, because this is something that happened when I was in junior high or high school. And that is that the product of this quarry is largely crushed stone. And what do you use crushed stone for? Well, aggregate for gravel roads, gravel parking lots. You put it in concrete. You could put it in asphalt, but you wouldn't want to, because serpentine is kind of a soft, slick type of mineral and rock that doesn't make a very good surface for stopping a car on if it's mixed with asphalt. But back when I was in junior high or high school, I can't remember, a local science teacher whose kid I actually was the same age as me, found out that there was asbestos in the serpentine from the Hunting Hill Quarry. Well, at that time, there were gravel roads all over Montgomery County and big parking lots. And so there was all of a sudden this enormous outcry. Parking lots were fenced off. Roads were, scraped off. This stuff was, had asbestos in it, for goodness sake. It's got to be dangerous. Well, that all sort of faded away with time, but they did discontinue using the aggregate, the crushed stone from Rockville crushed stone, for those kind of purposes. And now, as far as I know, it has two major purposes. One is to add to cement to make concrete, and the other one is to use a very finely crushed version of the serpentinite for the underlayment beneath patios, between slate and brick patios. Having used it myself, it compacts wonderfully. It's a phenomenal material for that purpose. And those of you who have been in the quarry back in the day might have had this problem. I certainly had, and that is that when you're driving around in the puddles on the quarry floor and you get all this stuff splashed up under your car, if you don't wash it off that day, basically it kind of sets up like concrete on the bottom of your car. Anyway, back to this. These beautiful grossular garnets are really the main beautiful mineral that people go after when they have the chance to collect it at the quarry. By the way, somebody asked earlier, how many minerals are there in this particular quarry? And I quickly jotted down 13. So there's certainly probably double that. Anyway, so here is the subject of tonight's talk. This beautiful, beautiful rock, often confused by people who don't know it with unakite, which of course is kind of similar. It's got some beautiful green minerals and pink, but this is not unakite. This is a metagabbro. So those dikes that we saw cutting into the serpentine used to be a rock called gabbro. And through the alteration of high pH, that means not acid, but basic, and a lot of water, the original minerals have now become this green mineral, which is diopside, maybe, and some pink minerals that are clinozoisite. And then you see some beautiful cinnamon color, like those garnets we just looked at, and that is grossular garnet. And it is, in fact, cavities that have formed along the edges of this material and within it that produce those pockets filled with calcite that the clinozoisite come out of, and as well those beautiful gemmy garnets. So how do we pronounce the name of this rock? So the rock, was first described from the River in New Zealand. So that river is actually the name of an area, a place in Essex, England, near a place called the... So looking it up, R-O-D-I-N-G is apparently pronounced either roding or rooting and not rotting. Okay, get it? So I think it's probably pronounced something in between roding and rooting. If you can think of like a Scot, an Englishman saying that, I'm not even going to try to say it myself, but it's not rotting, R-O-D, rod. I'm going to call it rodingite for the rest of the talk, and I think that's relatively close. So now we can say the name of the rock, and it forms, as I said, from the alteration of a gabbro, which is a coarse-grained rock similar to basalt with plagioclase, feldspar, and some dark minerals like amphibole and pyroxene, and it's produced by the release of water-rich fluids high in pH, that means not acidic, but very basic, and a lot of calcium in there. And that's called the serpentinization process. So Rodingite now, after those minerals have been converted via the metamorphic process, are primarily made of grossular garnet, as we said, diopside, zoisite, clinozoisite, idocrase, and prehnite. So here's a wet piece of Rodingite, particularly nice one. And you see this beautiful green mineral. And this green mineral is really the subject of the talk today. Here's another beautiful piece with a lot of the green mineral, which I grew up knowing as chrome diopside. And people said that because that's what our friend Larrabee said in 1969 in his publication. And the neat thing is when you find a piece like this and you look at these green crystals, and this is 4 inches across, so this is easily a big 1 inch plus crystal. When you see these and you sort of move it in the light, you see this sort of sheen come off it, or it's almost a Schiller effect, like a labradorite that you guys all know. So you get this sheen off of this mineral. Well, I wonder what causes that. But anyway, for most of my life, this was chrome diopside. Here's some beautiful grossular garnet surrounding it, and a nice, very nice piece of Rodingite that, you know, would be similar to the little pieces that we would have picked up in a gravel parking lot when I was a kid. So what is diopside? Well, if you look in the yellow part up here in the upper left, you can see that diopside is magnesium, calcium, silicate, silicon, and oxygen. And this is Larrabee's actual analysis of the diopside. And I added the chromian here because technically, if it's got chrome in it, it's a chromian diopside. So let's just look real quick here at the composition that he has. About 49% silicon, 5.5% aluminum. Well, that's very interesting because if we look at the formula for diopside, we don't actually see any aluminum in here. Well, it's actually true that you can fit some aluminum into a diopside crystal, but we'll talk a little more about that later. And then over on the right is actually his analysis of the grossular garnet. And you notice there's a whole bunch of aluminum in the grossular garnet, which there should be. And then you go down here and you see, oh, look, chromium, 1.15% in the diopside. All right, that makes it a chromium diopside. Let's not forget this 49% silica and this 5% aluminum. So that's why everybody said it was chromium diopside. So although I don't really make micro mounts, we do make what are called petrographic thin sections. And a petrographic thin section is a very, very thin, 30 micron thick slice of a rock. So when we had the opportunity to go to the quarry the last time I was there to collect a bunch of boulders of this stuff to make into tumbled stones to give away at a congressional open house night at the museum, we wanted to feature, the whole idea was we would feature a local rock. And I can't think of a more beautiful local rock than Rodingite. And so we got some from the quarry. And I kind of decided we better know what we're talking about. So we made some petrographic thin sections of the rock, and here's what it looks like. This is 500 microns, that's 0.5 millimeter. So this is about maybe 2 millimeters from left to right in this image. So this is kind of a micro mount. But what we see here is a big bunch of this clear stuff. And then what in the world is this over here? Well, under a petrographic microscope, if you introduce a polarizing filter, minerals like garnet turn black. No light goes through them. And other minerals like diopside and olivine produce these beautiful, what we call interference colors. And you can see those on either side. And this big area here is actually garnet. Now, in a petrographic thin section, the minerals are so thin that any color in that garnet, that cinnamon color, is you can't see it because it's the thin section is so thin. So we better analyze these, right? So we have a wonderful array of analytical equipment in the Department of Mineral Sciences, and it includes analytical SEMs. And an analytical SEM takes a beam of electrons, and that beam of electrons hits your sample like a thin section in a very small area, just a few microns maybe across. And what happens is a whole bunch of things, there are interactions that happen with the sample from these electrons impacting the material. Some electrons come flying off. Some light is emitted from some minerals. That's called cathodoluminescence. It's kind of like fluorescence. But the one that we really want to use for analytical purpose are the X-rays. And the X-rays given off from a material have energies that tell us about the elements that are in that material. So if we can sort out the energy of the X-rays, we know what elements are in the material and how much of that element are in the material. So let's dig in deep and take a close look at the diopside, the chrome diopside. Oh my goodness. Well, that's it. This is 300 microns. So the width of this says right here, 700 microns. So that's not quite a millimeter across. That's still not very high magnification, but look at what you see. The chrome diopside isn't a mineral. It's more than one mineral. In fact, just looking at this picture, we can tell from the grayscale differences in this electron image that there's a almost black one, a dark gray, and a light gray one. And not only that, but the beautiful layering here has been deformed as things happen in metamorphic rocks. You get lots of squeezing and deformation. And so this mineral, which may have had just beautiful parallel layers of these other minerals, now has this beautiful bent and deformed shape. Here's a close-up. There's the three minerals. This isn't chrome diopside at all. And probably, if you ask me, the reason that we see that sort of sheen coming off of this mineral is this group of minerals is because it's actually a bunch of layers, and the light comes off in ways that are affected by this layering within the minerals of what we used to call chrome diopside. Okay, so let's look at the analyses. So here's the first analysis. And this is the energy of the X-rays coming off. So right here at somewhere around 3 3/4 kiloelectron volts, we see a calcium peak. Over here, we see magnesium. Here we see silicon and oxygen. This looks like calcium, magnesium, silicate. That's our friend diopside. What's missing? There's no chrome. It's not chrome diopside, it's just diopside. So here's the actual analysis. when it's been converted from a spectrum like we just looked at into an actual chemical analysis. So we typically in geological circles, we express these different cations, the positively charged element like magnesium, as an oxide. So magnesium oxide, aluminum oxide, silicon dioxide here, calcium oxide, iron oxide. So we express those as oxide, weight percent. And these are those weight percents. But what's even better is we can then convert these weight percent numbers to the number of cations in that particular analysis of that mineral. And the cations are, as you see in the formula here, CaMgSiO. These are the cations, calcium, magnesium, and silicon. So if we count those, there's 1, 2, and there's 2 silicon, so 4. So if our analysis is really good, then the number of cations that are calculated from this analysis should be right around 4. And sure enough, there it is, beautiful 3.98. I call that 4. And there's no chromium. Looks like a nice diopside analysis, but there's no chromium. Well, what the heck? Remember, back in Larrabee's analysis, there was 1% chromium in the diopside. And also remember that the silicon value was below 50. And here we have 54, probably should be maybe even 55 weight percent silicon in a perfect diopside analysis. But there's a little bit of aluminum in here too, and that substitutes for silicon. So it looks like we have a very nice analysis of diopside, but what about the chromium? Well, was Larrabee mistaken? Was that a bad analysis? No, I don't think so. So here we go. This is another mineral in that layered thing that we were looking at a minute ago. And this is calcium with a bunch of aluminum and magnesium, some iron over here. And whoop, there's the chromium and a little titanium. Well, this is actually the grossular garnet. Son of a gun. The chromium looks like it's in the garnet. But let's take another close look. Here's the grossular garnet formula right in the middle. And if we count the number of cations, there's 3 calcium, 2 aluminum, 3 silicon. So that's 8. If our analysis is really good, and we notice that there's a whole bunch of chromium in this garnet, 9 weight percent, that's a lot. If we look at the cations in this analysis, converted from the actual analysis, it should be 8, and it is. So that, my friends, is the story of chrome diopside from the Hunting Hill Quarry in the Rodingite. Beautiful, beautiful mineral, but it's not chrome diopside at all. It's a chromian garnet. And so you wonder what the third mineral might be, this dark one, and it turns out to be a chlorite mineral called clinochlor, a magnesium silicate. So there you have it. The brightest thing is actually chromium grossular garnet. The medium gray stuff is nice, very nice diopside. Why is it green? Probably from the iron in it, not from the chromium. Chrome diopside is actually a common mineral in very deep rocks from the mantle, but the chromium diopside is a bright emerald green. It's not this sort of more pistachio green that the diopside, and now that you know there is not a diopside crystal, but it's actually a group of minerals forming something that looks like a diopside. And so there it is, not diopside, but three minerals packed into one in a beautiful layered effect that probably gives it this wonderful sheen. And that's my story for today. So if anybody has questions, I'll be happy to pull the slideshow back up and talk about this stoichiometry and analytical stuff, and maybe try to make it more clear if you have any questions. But that's the story. You never know until you look really close. How many people have actually been in the Hunting Hill Quarry besides myself? Andy, Kathy, Jeff.
So can I share something?
Sure.
Dr. Rose, I remember I volunteered in the mineral gallery when you were passing out all the little tumbled, most of them were cubes of Rodingite. And that was a very good crowd, very interesting, nice outreach from the science department. But Hunting Hill, here we go. Tons of grossular garnets. And then I guess the green would be the Rodingite, right? You're teaching me?
No, that rock in your hand is Rodingite.
Yes.
The rock, but the different colored things are minerals, or as we now know, the green stuff is a combination of grossular, chlor, and diopside.
Okay, and then what were you saying about Cummingite?
Coalingite.
Coalingite.
Yeah, Coalingite, as in Coalinga, California, where it was first described.
Okay. So I'm a micro mineral collector, but but here's—
You got a big piece?
These are my self-collected grossular garnets, and I never trim this specimen because I don't know how to trim it. This I just put in my sunroom, so it always has full sunlight.
It's not an easy rock to trim.
That's why I just left it. I'm going to put this on display. As I ran during your talk downstairs into my rock collection. I found this and I decided this goes on display in my little cabinet.
I'd like to see it in person.
Okay, well, next time I come into the museum, you're there, I'll bring it in. Great talk.
Tim, a question for us, Carl Miller. Thanks for the invite. Really interesting, collected there. Gosh, literally, I think I probably collected at Hunting Hill 100 times. So is the end result then that the rock, so you kidded yourself, you kept calling it a mineral, but is it that the rock Rodingite is no longer Rodingite because the composition does not include chrome diopside?
No. It is Rodingite. The rock
it is still Rodingite. Okay.
Absolutely. But what we always knew, and probably you always called chrome diopside, this beautiful green mineral, turns out to be not chrome diopside. It turns out to be a combination of three minerals, including not chrome diopside. So there is diopside in there, but what I didn't full circle back to Larrabee's original analysis, but basically when he analyzed the diopside, he took chunks of the green stuff, right? And analyzed that, thinking that it was monomineralic, that it was just one mineral, when in actuality, we now know it was three. And that explains the strange composition that he had. As I was trying to tell you, but I kind of failed to close the loop here, is that if we look at that original composition of Larrabee, it had too much aluminum in it, right? To be a diopside proper. And so remember what he analyzed was a chunk of the green stuff. And that green stuff has, we now know, grossular garnet in it, which is full of aluminum. So his analysis was perfectly fine, but it's not an analysis of a mineral. It's analysis of a combination of minerals that look like a single green mineral that we used to call chromium diopside or chrome diopside.
Yeah.
But it's still,
no, I followed
still
that, but I wasn't sure. So there's a part two to what my question was. So I wasn't sure if what I said just to you a moment ago was part of the conclusion. I understand it's not. You're saying it's still Rodingite. So here's kind of part two. I can't tell you who this was, but there was 2 or 3 geologists who were at the quarry one of the times that I was there back in probably the late 2000s. And, there was all of us mineral and crystal collectors, and they were interested in that, but they were more interested in the geology. And part of the conversation that they had was that calling that rock Rodingite actually wasn't correct, because Rodingite has a specific composition, and no matter what the minerals in that rock there were, it quote unquote didn't equal Rodingite. Frankly, I have no opinion. I'm just curious as to whether or not that comes into play here in this at all.
I can't tell you what they were thinking. The definition of Rodingite that I know fits this rock perfectly. It's found in other places around the world. It looks similar to our Rodingite. Maybe they know something I don't, but I think that it is Rodingite.
Okay, yeah. So thank you. I appreciate it. Like I said, I thought the conclusion that was being drawn was kind of ironic considering that conversation, but I get the point now. So if I find something about that, I'll ping you or ping the club and they can pass it on to you.
Okay.
Let me ask Tim about the status of people getting in there and collecting. And it sounds like if you went in with a geology group or something, you might get in, or but not maybe.
I have no idea. We were let in as Smithsonian employees, government employees, to specifically collect Rodingite. And we drove to the bottom of the quarry. This was all arranged through our education department. Someone in our education department contacted them. The quarry gave us the okay. The quarry is now only open, or at least when we were there, it was only open 4 days a week. They just, they don't have the demand for the aggregate anymore. And we went on a Friday. We drove to the bottom of the quarry, parked the cars on a Rodingite dike, literally filled the vehicles with chunks of Rodingite and left. And so it was a surgical strike to get some chunks of this rock. And that's the last time I was in the quarry. And I don't know anything about getting in. It's probably worth a try. I don't have a contact there anymore. There was a fellow named Paige Herbert who was a good friend of local clubs and would let us in regularly back in the 1980s. And there's actually a memorial stone to him at the entrance of the quarry. So if we had another one like him, we might be able to get back in. But as far as I know, we got in basically on this mission to collect this material, and we just went in, came back out. No time for collecting.
Yeah, like Kathy, I also when we were volunteering at this, a nice piece of the material you were handing out that day.
Did you remember what what the occasion was that we were handing
It was,
out?
I think it was underwritten by the National Crushed Stone, Sand and Gravel people.
Okay, okay.
And
So
You remember, Kathy?
Yeah, it was, well, Adam Blackenbicker was from the education department. He's the one who brought us all the material to hand out, but it was public outreach.
So we did use the Rodingite for a congressional open house, but I guess we weren't giving away pieces of it that night. We just had some big chunks of it sitting on the table for kids to look at and spray water on to make it look prettier. But yes, that's right. The National Stone, Sand, and Gravel Association helped fund our exhibit hall, and that was the last gasp of their sort of funding help that sponsored that giveaway.
Yeah, it was a good event.
So back in the, I guess, the late 1980s, because that's when I remember collecting with Fred Schaefermeyer specifically. And Fred also put together an entire suite of the rocks and minerals of Hunting Hill Quarry back in the day, and he left it with the management there. It'd be kind of neat to follow up and see if it's still there.
Yeah, they used to have on Earth Day, they would have little mini buses, and you could go over to the quarry and they would drive you down. You couldn't get out. They would drive you down to the bottom of the quarry, and then you could get out at the top. And there was Fred with his 2 tables with mineral specimens spread out, teaching everyone about what the minerals were. And he was there year after year.
We'll have to look into it, but I believe there's a Hunting Hill open house day. I may be wrong, but I remember seeing it and talking about it in our Montgomery County club. I know Gary and Diane are here. Gary, do you have any information on that?
No, I don't. I've lost my video too.
That's okay. We can still hear you.
Okay. Yeah, I know I've been back in there, a number of times a long time ago, but I think there was some special event they were going to do.
Well, it sure would be nice for us to get back in there because it's right in Rockville and it's so close to where we meet in our Montgomery club. I have a show and tell piece. It was given to me, but it's, how do you say it, Tim?
Coalingite.
Coalingite or coalingite?
Coalingite. It's after Coalinga, California. So
Okay.
I've always pronounced it 2 syllables, coalingite, instead of coalingite.
That's a nice,
that's
big,
a nice one.
big chunk. Yeah.
It's not a common mineral. It's really kind of cool.
The last but not least is a zonodolite. I don't know if you can really see the fibrous, but it's very much like an asbestos mineral. And this was collected by Fred Parker. Still have his little label. Yeah, Fred Parker. Yeah. There it is. Sorry about that. Zonodolite. It's probably coming out backwards. So anyway, a fantastic specimen.
Oh, interesting.
That's a beauty.
Yeah. I'd sure like to get in there and do some collecting. And somebody did put in the chats that there were 60 minerals from Hunting Hill, which is a large number. Most of the quarries that we go into, you're lucky to find 20. Actually, most of them you're lucky to find 10 or 14. Not quite the Franklin mineral with 435 minerals, but it's still 60 minerals is very large amount.
Whoever posted that, where does that number come from? Is there a publication that has a listing like that?
It was me, Tim. This is Carl Miller again. You can find it several places. I think including Mindat. I believe reference it. But there's a there's a book that was that has Maryland minerals and mineral locations, and I think that book said like 48, but that book was, you know, printed 30, 40 years ago. And there, I also mentioned in there, there's several minerals, several additional quote unquote minerals, bear with me, that are discredited, that were found there. So if you count all of them, it's approaching like 65 or 70.
I'm looking at MnDOT right now, Hunting Hill Quarry, upper section, Montgomery County, Maryland. It's listing 60 valid minerals. That's quite a few.
Yeah.
Tim, I have a question for you. Following up on Ken Reynolds, his first specimen that he showed, and one that you also showed, the coarse-grained. When you were describing it, you described it as having a brassy or a bronzy sheen to it. Do you recall offhand, or what that is? That grossular garnet? Do you have any idea what mineral that might be? Looks kind of golden.
So the cinnamon colored material is typically grossular garnet, and the coarse-grained kind of looks like that, but it's a metallic appearance, and not really translucent at all. So it's kind of flaky, almost micaceous. So it's very easy to tell them apart. Does that answer the question?
Well, my question was, what is that bronzy material? It's not grossular garnet, you said, but what it is unclear to me. And not that you're supposed to
It's the mineral coarse-grained.
Okay, thank you.
Yeah, it's the mineral coarse-grained.
So are you saying the garnets are in coarse-grained?
No.
Okay.
They're not associated.
Okay, thank you.
That I know of.
I'm going to ask maybe the same question as Carl had, but I'm still confused, or maybe it's a side question. You're saying that there is one mineral that is composed of 3 minerals. Now, doesn't that violate some sort of law somewhere?
Yeah, no. What we used to call one mineral, and clearly what our pal Larrabee thought was one mineral,
right,
is actually a mixture of 3.
Okay.
And that's what we saw in those beautiful images showing the layering within what we used to call chrome diopside, but we now know is actually a mixture of 3 minerals, which technically would make it a rock, right? It's a mixture of minerals. So that green material being a mixture of minerals is in itself kind of a rock, even though it's part of the rock Rodingite. But yeah, no, we can't call that green stuff a mineral anymore because it's not one mineral, but it's 3 combined.
Then wouldn't that mean that Rodingite is discredited?
No, because Rodingite is it doesn't depend on that mineral per se. Rodingite is metamorphosed gabbro, where the minerals have been changed from their original mineralogy to a mineralogy that includes grossular garnet, diopside, clinozoisite, zoisite, and there were a couple other things that I had on that list. And those are all still there. So it's still Rodingite. It's just that this one mineral that we used to think was, now I just said it, this one green material that we used to think was a mineral is actually not a mineral, but it is a combination of 3 minerals.
Okay. There's still something that is not quite
so
making it, but I'll think about it. Thank you.
I think what it might be that your Beth is that Rodingite is not a mineral, it's a rock.
Yeah.
Right.
Yeah.
Okay. I can handle that. That makes sense to me. But
so we have a rock within a rock.
In a way, in a way, the green material, if you just had a piece of that, it's not a mineral, it's a rock made of 3 minerals.
Okay.
Even though we used to call it chrome diopside.
Okay.
Hey, Tim, I don't claim any special knowledge because of my last name about the makeup of rocks. But obviously the access to your analytical equipment was very key to you uncovering the mystery of the 3 minerals in one. Can you talk about some of the common tests you do day to day with the various analytical types of equipment that you have access to? What do you do most often?
Most often it's relatively mundane. We have 3 electron beam instruments. One of them is called an electron microprobe. It's very good at coming up with very high quality analyses of rocks, minerals, or glass, minerals, other materials. I recently, just last week and over the weekend, was using that to analyze little grains of glass from explosive eruptions of Kilauea volcano in Hawaii. People right now at this very minute are using that instrument to study the products of experiments that some of our scientists do in special apparatus that can actually produce temperatures and pressures that replicate conditions in the crust of the earth and as deep as the lower mantle. So they're studying these experiments that they have done to try to prove a certain condition that occurred in the earth, either in the crust or in deeper, in certain very specific conditions. We also study meteorites routinely. One of the most exciting things that has come to the labs recently are new samples of lunar soil that NASA just released back in the spring, I believe, of this year to a group of scientists, including some of ours. And so some of our folks actually were the first people to touch those grains because they had to make special mounts, like a thin section, like I showed a picture of. And I've seen some of those grains. And the funny thing that we noticed the other day is that there's actually some similar looking grains from the lunar soil compared to those Kilauea explosive deposits that I've been studying. So, of course, these glass particles on the moon are produced by impact melt, and the melt from Kilauea is molten magma from deep in the Earth's crust. But there are some very interesting features that have never been explained by anyone. And we see them in both these new lunar, what they call regolith, which is soil, the fluffy stuff that the astronauts left their boot prints in. You've seen those pictures. Well, NASA has been sitting on a bunch of those samples for quite a long time. And I'll tell you just for fun that I am involved in a study with some of our anthropologists on the history of dentistry. And we have looked at fillings in teeth from people from the 19th century. So I study dead people in a way, but really we are studying the composition of the fillings that are in the teeth of these people who have allowed us to borrow them temporarily from the cemetery, or in the case of the Confederate submarine, the Hunley. The men of the Hunley, we know the exact day they died, so we know that the fillings in their mouth had to have been made before that very date. And that has been very helpful. And in fact, we found in some of those fillings by doing these same analyses that perhaps some dentists were starting to make amalgam, which is that mercury silver compound that I have a mouthful of. And they were adding the correct things, copper and tin, to prevent the mercury from leaching out of that amalgam as far back as the Civil War, which is kind of surprising. So anyway, I'm telling you this because I just had a crown put in. And when I went to the dentist, I said, "Can you save some of the amalgam from my tooth?" And sure enough, he did. He saved some chunks. And I was able to actually look at my own amalgam to compare to the amalgam that I've been looking at from 19th century and early 20th century people's teeth. And it was actually quite revealing. But that's a story for another day. But recently, I actually studied my own tooth filling.
So were there traces of mercury in it?
No, not traces, a ton of mercury.
Right.
But the good news is there was no mercury by itself, no free mercury. That's what we want to worry about, right? So, like I said, this is a story for another day, but if you know about how amalgam is made, and I can remember seeing the dentist actually mixing it behind my back while I was waiting for my cavity to be filled. They mix a combination of powdered silver with copper and tin in it with liquid mercury. And you mix it quickly because you have a few minutes to work with it. They press it into the cavity that's been cleaned out and they form it. And lucky for us, because you put copper and tin in with the silver, those two elements scavenge mercury. So as soon as any free mercury were to become available in your filling, it is immediately glommed onto by copper and tin. Now, this is my opinion. Some people will say that I'm full of it, but I did not see any free mercury or any evidence of mercury leaching out of my filling. And so this is not to say that we know very well that some of the early amalgams were nothing but silver and mercury, and those fillings did in fact make people very sick.
Now, if they could just figure out why every one of my teeth that has a filling has cracked, broken in half, or whatever it's the dentist pushing too hard, or if it's just the crack just extends itself through the tooth. I don't know.
Yeah, the one that I had to have repaired was cracked up like that, and a whole corner of it came off one day while I was eating tortilla chips. But anyway, that's what led to the study of my own tooth filling and learning more. It's surprising the textures that you see in the amalgam, and it actually does help me understand what I'm looking at in these 19th century fillings. It is now giving me a better understanding. So in the National Museum of Natural History, you never know what you're going to get involved with. That's a recent one that I thought might kind of tickle you.
Very interesting. Tim, can I pat ourselves on the back? I think one year you used the $1,000 we gave you to go to a conference to help you use some of these machines.
Indeed.
Yay, yes.
Indeed. Yep. We've continued to go to these conferences. We had several that were virtual during COVID. You know, the show must go on, and we continue to attend these meetings. It's how we keep up on what, you know, new developments there are in the technology. so that we know better how we can do analytical work for the scientists that we're working for.
If we have another minute, can I ask you a question about moon rocks?
Sure.
I noticed in the, I think it was in the Air and Space Museum, that they have a moon rock you can touch that's like embedded in a podium, and it's black. But when you see the pictures of the moon, there's usually white powder all over the place. I think they even have a photograph of the black rock sitting on the surface. Do you know what the difference in composition is, and why most of the moon is white, but there's those black rocks there?
So a lot of the moon is basalt, and basalt is a very dark color. It's really a dark gray, sometimes black rock. But I hate to tell you, but when people touch rocks in our exhibit galleries, they get really grimy.
I noticed the Mars rock is also black.
Well, that one is actually black. That's a different kind of rock. Well, not terribly different actually, but that is a very different rock. And it was black when we put it out there. But one of the things we learned when we took apart the exhibit hall that we replaced, oh my goodness, 25 years ago, was that touchable rocks need to have a polished face on them. Because if they don't, they just get grimy. And I will tell you the whole story. There was a black grimy rock in the lunar gallery in the old exhibit hall. We took the brackets off and turned it over, and it was this beautiful banded black and white rock. So when it was put on exhibit, there was this beautiful black and white banded rock with a big fold in it like that. And it was big like that. And I was shocked. We took it off and flipped it over, and what was just grime, black, gray, stuff from people's hands had built up on it to the point where you couldn't tell what kind of rock it was. So if you go through our exhibit gallery now, you'll notice that the rocks that say, please touch, all have a big polished face on them. And that's because grime doesn't stick to a polished face. In fact, I think people actually wipe it off. If anything sticks, it gets wiped off. But unfortunately, if you look like around the edges of the polished face, you'll see that grime build up. And there are a few samples in the exhibit hall that we do have to periodically take off of exhibit and scrub the grime off. But the rock at Air and Space from the moon, it might be a little grimy, but anyway, there's some inside museum stuff that probably I shouldn't have told you. Anyway.
Well, that's not surprising to me at all. But I went to college in Houston, and my alma mater now has a moon rock, and it's encased in acrylic. It's very, very light color.
Well, remember, the moon also has a rock type called anorthosite, which is mostly white feldspar.
Feldspar. Okay, so feldspar is basalt.
Yeah, sure. There are white moon rocks.
Okay,
but a lot of basalt too. So there are black ones and white ones.
Basalt.
And remember, the whole thing's covered with this lunar regolith, the soil material. So when you look up there, are you actually seeing, rocks, or are you seeing dirt?
Dirt. Gotcha. Just like here.
A lot of dirt.
Oh. Okay, thank you.
Yep.
As a quick footnote to that theme, the Rosetta Stone has been in a British museum for a century or so. I think Napoleon's guys captured it and brought it back from Egypt. They thought it was a black basalt or something like that. It turns out it's actually a much, much lighter stone they discovered, is filled with grime for like a century, and nobody knew what it was. So just
how could that possibly happen, Andy? I just don't know. But you can't touch it now, but maybe they should have let people touch it and it might have wiped it off. I don't know.
Tim, along that same line, I'm a volunteer at the Geology Gems and Mineral Hall, and one of the things that always is a sure winner with guests, visitors, is I invite them to be sure and touch the piece of Mars, and it's a good story behind it, and I congratulate them on touching a piece of another planet. Then I usually, but not always, add that, well, in fact, you're not really touching the stone, you're touching the grease and dirt and grime from other people's hands. It always gets a laugh. But as long as we're on the topic, it raises the question, is that little slice ever cleaned?
I don't know the answer.
Everyone likes touching it. Kids, babies, old people, medium people, foreigners, US people, everybody loves touching it.
Well, that was our one-upmanship on Aaron's base, right? The moon. We've got Mars.
Multiple pieces too, of the 100 and some odd that exist or that are known.
Yeah.
And those are meteorites, right? Like we didn't collect them from there. They fell to Earth, and we somehow figured out that they came from Mars, right? Because my family had a discussion about that too.
Yes. I'm not a meteoriticist, but they assure me that they are very, 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 very confident that those rocks are from Mars. We have yet to
being the
bring
only
anything
planet.
back.
Mars is the only planet known to be inhabited only by robots.
Tim, I had one question before we go. You said that the Schiller effect from that one example of the Rodingite that you had.
The green stuff.
The green stuff. It almost looked like it was in plates. Is it micaceous in any way, or is it?
Well, it's not really micaceous, but you saw the layering of the three minerals. I would expect that the reason it looks platey like that is that it breaks along the crystal boundaries between those three minerals, and they're not always super deformed and bent like in the pictures I showed. I suspect there are some that are more just flat and haven't been deformed as much. So does that answer the question?
Yeah. Yep.
Yeah.
I also remember from John Wiedner's presentation that he did for our Montgomery County Club on garnet. Garnet is not actually one mineral. It's a combination of many minerals, and it can be a variable in each garnet to make it a little different. So kind of explain Rodingite too.
There's a lot of different garnets.
Yeah, Ken, not a combination of different minerals, but there are many, many forms of garnets, and they can slide in composition from one end into another.
Gotcha.
So those were all of the examples we were looking at then.
Yeah, right.
Well, Tim, thank you very much. That was an excellent presentation. And
oh, you're welcome. I'm always happy.
Enjoy having you. So thanks again.